Gather round while I sing you of Wernher von Braun, a man whose allegiance is ruled by expedience. Call him a Nazi, he won't even frown. Nazi schmazi, says Wernher von Braun. Don't say that he's hypocritical, say rather that he's apolitical. Once the rockets are up, who cares where they come down? That's not my department, says Wernher von Braun. Some have harsh words for this man of renown, but some think our attitude should be one of gratitude, like the widows and cripples in old London town, who owe their large pensions to Wernher von Braun. You too may be a big hero once you've learned to count backwards to 0. In German or English, I know how to count down. And I'm learning Chinese, says Wernher von Braun.
To the engineer, spaceflight poses two problems. The first is, of course, to build a rocket ship. The second, and no less important, is to prepare and train the men who are to fly the future rocket ships and to provide suitable working conditions that will enable them to survive in space. To help show you what is being done to solve these problems, we have called upon one of the foremost exponents of space travel, Dr. Wernher von Braun, who is at present the chief of the Guided Missile Division of the Army's Rocket Center at Redstone Arsenal. He was also overall director of the development of the original V-2 rocket.
The training methods for future space flight and the special equipment needed for survival are much like those of present high-altitude flying. And the experiments we are making today are helping us to solve the more complex problems to come. Take the present-day pressurized flying suit, for example. It has been designed for use at extremely high altitudes and is a forerunner of the suits we will wear when we make that trip to the moon. To give you an idea of how engineers and medical men are working hand in hand, here are a few examples of the research that's being conducted at this time. This pressure suit is being worn in a test chamber where the air pressure can be dropped suddenly. Notice that the water boils at this low pressure, even though it is only at normal body temperature. Blood would do the same without the protection of the suit. In other tests, without the suit, where the drop in air pressure is less severe, we see that the body still reacts violently to a sudden decrease in pressure. Lieutenant Colonel John P. Stapp of the United States Air Force has subjected himself to the tremendous forces of a rocket sled that reaches a speed of over 632 miles per hour. The sled stops so quickly that Colonel Stapp's body becomes 35 times heavier than normal. From these tests, we have learned that men can take much greater acceleration forces than crew members of a rocket ship will undergo on a takeoff. Today's aircraft are so fast and so complicated that it has already become routine to train the crews on the ground without risking lives or equipment. This is done with a device called a flight simulator. Here the crews experience all the sensations of an extended flight. The crews of future rocket ships will train much the same way. We will use a simulator on a centrifuge and employ an astrosphere to train the celestial navigators for our coming space flights. Now here's a model of my design for a 4-stage orbital rocket ship. Compared to the unmanned instrument rocket, it is quite large. But the overall size and weight of the rocket is mainly determined by the 11 tons weight of this top section. This weight dictates the amount of fuel and the numbers of motors needed to produce enough power to equalize the gravitational pull of the Earth. The payload in the top section will consist of 10 crew members plus equipment. Notice the wings, small rocket motor, and landing gears. This is a section that must ultimately return the men to the Earth safely. To produce the energy needed to hurl this stage into the orbit, we need these 3 additional rocket-powered sections. Here we have a cutaway drawing of our rocket showing the location of the fuel and the motors of each section. The first stage carries 1,060 tons of fuel, and its 29 motors will lift the entire weight of the ship vertically off the ground. The second stage has 8 motors and carries 155 tons of fuel. It will be dropped when its speed has reached 14,300 miles per hour. The next is our third stage, with only 1 rocket motor and 13 tons of fuel. The third stage gives the passenger section the final kick to attain the orbit. It will not be separated from the passenger section until just before the return flight. The third stage will be left in space, and a very small motor in the winged fourth stage will return the ship to the atmosphere so it can glide back to the base. If we were to start today on an organized and well-supported space program, I believe a practical passenger rocket could be built and tested within 10 years. Of course, it would be foolish to rush headlong into building a 4-stage rocket, man it with a crew, and attempt to fire it into an orbit without first following a step-by-step research and development program. Let's illustrate this with the help of a few pictures. First, we would design and build the 4th stage, and then tow it into the air to test it as a glider. This would also allow the crews to practice. Next, low-altitude flights would be made, firing the small rocket motor in the 4th stage. This would also give the crew more and more training. Following that, the 3rd and 2nd stages would be constructed and tested very thoroughly on the ground, after which they would be joined to the passenger section so that faster and longer flights could be made, up to speeds of about 12,000 miles per hour. The only thing remaining would be the building and ground testing of the huge 1st stage. Then there would be no more test flights. When all the sections are joined together, the ship and its crew will be ready for man's first flight in space. Let's look ahead a few years and see how this might be accomplished. A voyage around the moon must be made in 2 phases. A rocket ship taking off from the Earth's surface will use almost all the fuel it can carry just to attain a speed great enough to balance the pull of gravity. Unpowered, it will then keep circling the Earth in an orbit outside of the atmosphere. This is the first phase. However, if we can refuel the ship in this orbit with fuel brought up by cargo rocket ships, it can set out on the second phase, the trip around the moon and back. To facilitate this refueling operation, we will establish an advanced base in the orbit, 1,000 miles above the Earth. This advanced base, or space station, will be headquarters for the final ascent to the moon. Our space satellite will have the shape of a wheel, measuring 200 feet across. Its outside rim will contain living and working quarters for a crew of 50 men. Just below the radio and radar antenna is the atomic reactor. Its heat will be used to drive a turbo generator, which supplies the station with electricity. Access to the station will be through an airlock in the hub. The 3 large spokes are elevator shafts, and the small pipes are used as condensers for the turbo generator and the air conditioning plant. The entire wheel will slowly rotate at 3 revolutions per minute. The resulting centrifugal force will produce an artificial gravity for the men in the rim. Notice that the floors are placed so that the men stand with their heads toward the hub. The wheel is divided into 9 sections. The first section is headquarters and communications. The next section will be for Earth weather observation and prediction. Military reconnaissance experts, aided by powerful optical and radar telescopes, will observe every point on the globe as the space station makes its complete trip around the Earth every 2 hours. Next is the emergency hospital section, and then the astronomy division, where men will keep an eye on the rocket ship as it makes its trip around the moon. The rest of the space station will house calculating machines, maintenance facilities, air conditioning equipment, living quarters, and even a botanical and zoological laboratory. This entire space station will have to be prefabricated and tested on the ground. After dismantling, it will be transported in pieces up to the orbit. For the difficult job of reassembling the structure, we have provided a new type of spacesuit. Using gyros and 2 small rocket motors, the operator can tilt and move in any direction. Located outside will be 7 remotely controlled mechanical arms, each a specialized tool. By rotating himself within the spacesuit, the operator can use any of the arms for the variety of tasks in assembling the space station. When the day arrives for construction to begin, the thousands of parts for the space station will be transported to the orbit by our multi-stage rockets. We merely replace the wing passenger section with a simple cargo-carrying nose. These cargo ships will be unmanned. A passenger rocket, 1,075 miles above the Earth, will guide each of the 12 approaching cargo rockets to their rendezvous in the orbit. This ship, which circles the Earth every 2 hours, will be the command post until after the space station is finished. On the ground, the first of the cargo rockets is ready for takeoff. When the guide ship reaches the correct position in the orbit, the cargo rocket is fired. While its motors are firing, the cargo rocket is controlled by an automatic pilot, like a guided missile. Up in space, the blast-off is observed with the aid of optical instruments. In the guide ship, the navigator locks his tracking radar on the rising cargo rocket. At about 24 miles altitude, the first stage breaks away and the second stage motors fire. 2 minutes later, the cargo head blasts away from the second stage and continues firing until its speed reaches 18,468 miles per hour. Automatically, the motor cuts off. Now, with the aid of remote controls, the navigator rotates the rising cargo rocket so that when it arrives later in the orbit, it will line up with the guide ship. Here, at 1,075 miles up, follows the most precise maneuver of the entire operation. The motor of the cargo rocket is fired again until its speed and course exactly match that of the guide ship. Radar remote control will enable this maneuver to be performed with a high degree of accuracy. 56 minutes have now elapsed since takeoff. The cargo ship is floating in space, 2,000 feet ahead of the guide ship. 2 crew members make their way to the cargo head to begin the unloading operation. First, the motor and tanks are detached. Then 2 bottle-type construction suits are removed from the hull. When fitted in the airlock, each of these construction suits will receive an operator. The sections of the cargo ship are moved back to make way for other supply rockets soon to arrive. Construction of the space wheel now begins. The sides of the cargo nose are mechanically separated. Built-in tanks of compressed air inflate this large plastic inner section of the hub. Thin metal plates are immediately clamped on the outside to protect it from meteors. The first workday in space draws to a close. Every 24 hours, another cargo rocket will arrive in the orbit. When the airlock is attached, the pressurized hub section can be used as temporary quarters for eating and sleeping. Each succeeding load is carefully scheduled so that the parts of the station can be assembled in correct order. Nylon ropes prevent the parts from slowly drifting away. Next, the atomic reactor is installed. The wheel begins to take shape now as the three main spokes and rim sections are joined together. Condenser pipes are fitted next, so that the atomic reactor may be put in operation. Even though there's no apparent motion, everything in the orbit is hurtling around the Earth at 16,000 miles per hour. The shell of the station is completed. Now comes the delicate task of installing instruments and the multitude of equipment inside. Finally, two small rocket motors on the rim, blasting for a few seconds, will set the wheel in permanent motion to revolve 3 times a minute. As life on the station settles down to routine, the large reflecting telescopes will begin their work. These giant eyes relay pictures to television screens inside the station. One telescope photographs the surface of the Earth. Another keeps a constant watch on the Earth's weather, while the third is trained on our next objective, the Moon. The primary purpose of the first Moon trip will be to test the methods and equipment to be used on later voyages into deep space. It will be essentially a scouting trip around the Moon, and no landing will be attempted. To understand the plan of the trip, let us use this model. Here is the Earth with the Moon circling around it. Since the first half of the trip will take 5 days, we must aim the ship well ahead of the Moon, so that they both arrive at about the same point in space.
I talked with Dr. von Braun earlier this evening.
We will go to the Moon again. There may be a 10-year gap or so, but when we do return to the Moon, we will go there with our reusable space shuttle, with probably a reusable 2-stage tug to fly from low Earth orbit onto lunar orbit, and land even on the Moon itself with a vehicle that can return to a lunar orbit to be fueled up and do that portion of the trip also repeatedly. The net result will be that transportation cost to the lunar surface will be down to maybe 1/10 of what Apollo demands. And so we can really think of far more ambitious lunar surface missions, such as a semi-permanent installation on the Moon, or traverses across the entire face of the Moon, maybe of several thousand miles length, where would land a crew in one corner of the Moon to pick it up a few weeks later in another location. I think all good things have an ending, and I consider Apollo a little bit, as it were, as the sailing ship and dog sled area to the South Pole. Well, next time we'll go to the South Pole, we'll go by turboprop airplane.
Mm-hmm. You said 10 years or so. You don't really expect anything like that in 10 years. You're talking a much longer period than
Not
that.
necessarily. You see, the reusable space shuttle will be available in 1978 with first successful flights, and it can very definitely be an operational vehicle by 1980, which is 8 years away, and 2 more years will suffice to go back to the Moon with the tug that is carried into orbit by the shuttle. So I'm not at all pessimistic.
When do you see man go into some other body other than the Moon?
Well, I think the next target for men, other than activities, of course, in low Earth orbit, of which there would be many, will probably be Mars. We have learned a great deal about the planet Mars during the last 2 years, particularly through Mariner 9, which mapped the planet Mars thoroughly and discovered a few geological phenomena on Mars that nobody had expected. For example, Mars has the highest volcano in the world, in the known solar system. That volcano is 16 miles high and has about a total volume twice as much as the largest volcano on Earth, which is the big island of Hawaii, which when measured from the bottom of the ocean is, I believe, only 11 miles high. So this is twice as big, twice as voluminous. And also there's every indication that it was active in a relatively recent geological period
just judging from the very few meteoric impacts on the crater rim. Now, another discovery made by Mariner 9 was a canyon on Mars. Imagine Grand Canyon stretching all the way from Miami to Seattle, twice as deep and twice as wide. That is a canyon that was detected on Mars. So this too seems to show that Mars is by no means a geologically dormant or dead planet, but apparently quite active. Now there's of course always a question of lack of water on Mars. There's no doubt about the fact that Mars by and large is pretty arid. But the combination of volcanic heat and of course also water vapor exuded by volcanic eruptions makes it entirely possible that there are oases on Mars where the environment is quite different from the average. You wouldn't expect by looking at the Sahara Desert that there could be oases with palm trees, for instance. And it is for this reason that many people believe that the likelihood of finding even some not very higher forms of life, but at least some higher forms of vegetation on Mars is quite good. Now, I think needless to say, if we do find evidence of life on Mars, the rush will be on again, and man probably wants to follow unmanned exploration. The first two Mars soft landers, unmanned, will be launched later this year and are scheduled to soft land on Mars in the summer of 1976, next year. So about a year and a half from now, we will be able to answer the question far more succinctly whether man will probably go to Mars. Let me say this, we made a study in NASA while the Apollo program was still alive on how we would send a man to Mars with modern technology. And a scheme emerged that looked something like this. You would build two interplanetary spaceships in a low Earth orbit from parts flown up there with a shuttle, modularized parts that are stuck together in Earth orbit. You would, of course, also fuel these two interplanetary spaceships with propellant brought up by the shuttle. These ships would have a nuclear rocket engine. NASA had developed, jointly with AEC, a nuclear reactor engine that is essentially a reactor that operates at 5,000 degrees with a lot of channels leading through the reactor through which you pump liquid hydrogen. The hydrogen is heated up to 5,000 degrees and then simply permitted to expand through a convergent-divergent nozzle. The exhaust velocity is about twice as high as that of a combustion hydrogen-oxygen engine, such as employed in the upper stages of Saturn V. So it's really a very fuel-economic system. And this nuclear rocket engine, one in each of these two interplanetary ships, would go through several maneuvers. One, drive the ship out of Earth orbit on a trans-Mars trajectory. And there would be a free coasting period, several months, by the way, going to Mars. Then the second maneuver would be the capture maneuver of the ship into a circummarching orbit. And the two ships would remain in that circummarching orbit, pretty much like we kept the Apollo Command and Service Module in orbit around the moon and made the landing with a separate LEM vehicle. You remember how it was done in Apollo. Now, there would also be a separate Martian version of the LEM, a chemically powered vehicle capable of making a soft landing on Mars and the upper stage flying back to the two ships left circling in Martian orbit for a rendezvous and docking maneuver. And this Martian LEM would then be abandoned, and the return flight would be conducted with the nuclear-powered ship again. There would be a third power maneuver driving the ships out of the Martian orbit, and finally a fourth maneuver capturing them back into the Earth's gravitational field, from which the crew would be recovered again with a shuttle. That's essentially the scheme. Now, such a program would roughly cost as much as the Apollo program, not more, but also not less. And I think it would probably not involve 3 people, but a dozen people going to Mars, because the travel time of the entire expedition would be on the order of 1.5 years. So you would like to take a cook and a doctor and everything else along. You know, it's a little more like an expedition on a sailing ship, times of Magellan. Well, I tell you, Women's Lib will see to it that, speaking of women, by the way, I believe that before the end of the century we're going to have a research station on the moon. There will, of course, also be lady scientists, and the first baby will be born on the moon before you know it.
I promised Dr. von Braun's secretary to get him in his car at 3:17.5, and since our clocks are not synchronized, I think we better quit now. Thank you.
In recent years, entrepreneur Elon Musk has put himself at the forefront of the emerging commercial space industry, with his company SpaceX enjoying multiple orbital rocket launch successes, as well as the development of their self-returning, reusable rocket systems. Just last year, Musk dreamt big when discussing the future of space travel, saying it was his goal to see 1 million people living on Mars within 50 years. But with a population that large, the logistics and planning wouldn't just involve space travel, but would also have to take into consideration a variety of social, economic, and political factors. For instance, who would be in charge? Who would be mayor, or governor, or president of the Red Planet? Never fear, the answer may have already been given to us. In 1949, rocket scientist Wernher von Braun, former Nazi rocketeer, soon to be NASA's star rocket designer, wrote a science fiction book about humanity's first mission to Mars. Von Braun put his considerable technical knowledge to use, according to many reviewers, perhaps adding too much detail, in writing Project Mars, a technical tale. In his story, set in the 1980s, 10 large spaceships make the journey, a project which required upwards of 1,000 flights into Earth's orbit in order to build, supply and fuel these 10 ships, and it is an international, cooperative project. By chapter 22 of von Braun's novel, the human visitors have discovered a peaceful indigenous civilization that resides underground on Mars. Remembering when he wrote it, little was known about the planet's habitability. And then, in chapter 24, we are given an outline of how Mars is governed by this civilization. It's here that we come across a wonderfully surprising discovery. The Martian government was directed by 10 men, the leader of whom was elected by universal suffrage for 5 years and entitled Elon. 2 houses of parliament enacted the laws to be administered by the Elon and his cabinet. The upper house was called the Council of the Elders and was limited to a membership of 60 persons, each being appointed for life by the Elon as vacancies occurred by death. In principle, the method was not unlike that by which the College of Cardinals of the Roman Catholic Church is appointed. Usually the Elon chose historians, churchmen, former cabinet members or successful economic leaders who could offer lifetimes of valuable experience. Yes, you heard von Braun, one of the progenitors of human space travel, correctly. The leader of Martian civilization is called Elon, the same name as Elon Musk, who is currently leading the field of human space travel. Predestination, time vortex, or just a delicious coincidence? Maybe throw this one in the Mars Weirdness file with Jack Kirby drawing the face on Mars in a comic 17 years before it was discovered.